It takes force to do work, and whenever work is done, it takes time. When we want to do work in as short a time as possible, we need to calculate power, the rate of doing work. But increasing power has its trade-offs. More power means more energy, so sometimes it may be worth taking a little more time to do the work and use less power. Any machine that does mechanical work needs to be rated according to the amount of power it can deliver. That ability then has to be matched with the amount of power needed to do the job in a given time. When James Watt invented his steam engine in the 1700s, he had to somehow measure the amount of work it could do. So he measured the newtons of force it could deliver, or the foot-pounds of torque it could apply to a shaft. But since the main advantage of his new machine was that it could do work faster than an animal, time had to be an important factor in his calculations. Work does not involve time, so it had to be a new idea. That idea is power, work divided by time. The unit of work he chose was the Newton meter, the unit of time, the second. And since James Watt came up with the idea, that unit of power is named after him, the watt. The problem with the watt, or the Newton meter per second, is that people at the time did not use those units to measure power. They were only concerned with how many animals it took to do the job. Well, since Watt wanted to sell his machine to these people, he came up with a unit that compared his machine to a donkey. A donkey was the main source of power in England during the 1700s. It can exert a force on another object, which is why they're useful doing work, when they cooperate. Watt figured that the average donkey could pull with a force of about 550 pounds and move an object 1 foot in 1 second. Now he had all the ingredients to measure power. Force applied through a distance is work. And since the work was done in a certain period of time, in this case 1 second, Watt now had a unit of power, the rate of doing work. For Watt, that unit was 550 foot-pounds of work done in 1 second. Either Watt loved horses or he hated the sound of the name donkey power because he called his new unit the horsepower. Too bad for the donkey. Horsepower was a unit that people could relate to, and one which we still use today. Horsepower ratings can be given for situations where straight pulling is useful. The faster we want to go, the more power it takes. Measuring power is also handy where straight pushing is applied. But in most cases, horsepower needs to be calculated right where it's delivered, usually through a rotating shaft. The calculation for power in a rotating system is the same, the time it takes to do work. Work in a rotating system is torque times angular distance. The time is still in seconds. The result will still be the same units, foot-pounds per second, which is usually converted into horsepower. But let's back up just a little. This formula for power, torque times angular distance over time, can be expressed in a different and perhaps easier way. Angular distance over time is a rate, like revolutions per minute or speed. So power can also be found as force times rate in the rotating system. That's torque times omega. Whatever method you use to calculate horsepower, the result is the same. You can either measure the amount of work being done and the time it takes to do it, or you can measure the force produced by the machine and its speed. Both methods are a measure of power. When power out is compared to the power in, you have an excellent way to measure the efficiency of the machine. Usually, power is delivered through a system of gears and linkages. However, some power is lost because of resistance of the moving parts. The result, say in a tractor, is that the amount of power that reaches the wheels is less than the amount of power put out by the engine. For Herb Cargill, understanding the power requirements of agricultural equipment is part of his job.
For a tractor to operate efficiently, we do two different things with it. One is a drawbar horsepower, which is the effort that the tractor can exert in pulling a load, such as a disc, a plow, a blade, a car out of the ditch, whatever. The other horsepower is a power takeoff horsepower that is utilized through a mechanical shaft to a gearbox, another hydraulic pump, a generator, an alternator. We can use this mechanical horsepower in different ways. Agriculturally, it's used to run choppers, rotary tillers, different types of farm implements. But two things happen. The power takeoff horsepower is generally greater than the drawbar horsepower. The reason being that the drawbar horsepower is transmitted over to the wheels, through the axles, and to the ground. Slippage occurs on the rear wheels in pulling a load. Consequently, the effective horsepower is a little less. For example, a power takeoff of this particular tractor, horsepower-wise, will be approximately 40 horsepower. The drawbar horsepower will be about 37.5 to 38 horsepower. There are several different methods that power can be transmitted or that we can use the power takeoff horsepower. Other applications would include mounting a hydraulic pump on the power takeoff. The power takeoff, the tractor horsepower, would then turn this hydraulic pump. That hydraulic pump could be used to run hydraulic cylinders, hydraulic motors, many fluid power applications. Many farms also have standby power. They take the tractor, hook it to a generator. If the power goes out, a power shortage for some reason, the farmer can still continue to milk his cows, pump his water, do his operation at the farm. Just the mechanical transmitting of power to a gearbox is only one of the applications that power takeoffs can be used for.
Technicians working with power conversion like transmissions, torque converters, and power takeoff must know the power at all points throughout the system. Too much power could damage the machinery. Too little, and the job is not done properly. Likewise, they need to know the efficiency, the power out compared to the power in. Here's an interesting project. Think about how many devices you use every day that develop power. We use power to push, pull, lift, and lower objects of different sizes and weights. We also do that work at different speeds. If you add up all the power you've used since you got up this morning, that's a lot of donkey power.